Welcome to part 1 of our lecture video series for Monday, March 20th, where we're going to begin with a warm-up. So let's look at an example of a chemical reaction and let's apply what we know about the law of conservation of mass to what happens in a chemical reaction. So here I've given us an example where we have a sample of coal that is reacting with pure oxygen gas in a sealed container. So we've got this sealed container that contains a sample of oxygen and surrounding it pure oxygen gas. Sorry, a sample of coal right here, surrounded by pure O2. Upon the combustion of both coal and oxygen, water vapor is formed as one of the products. So here we have the reactants, or at least our conditions pre-reaction. And here we have our products. Or our post-reaction conditions. Language. Which means that this arrow here is showing the combustion reaction between coal and oxygen. So this warm-up hasn't asked us of anything yet. So let's see here. Let's break it into pieces. A. If 100 grams of coal and O2 gas are reacted, what is the total mass of our products? So that means we need to compare what's going on pre-reaction and post-reaction. So recall that chemical reactions are simply just a rearrangement of atoms, meaning that they are not lost nor gained. And this idea of something being neither lost nor gained during some kind of change is what we call something being conserved. So specifically here, our number of atoms in total is conserved, and all of those atoms sum up to some total mass, right? That is an example of matter, anything that has mass. So this means that mass is conserved. So we have 100 grams of starting materials. They undergo some rearrangement as a result of those chemical bonds being broken and new chemical bonds being formed. And as a result, we have now new arrangements of atoms in our product condition jar here. However, the sum of all of those products should equal the same sum of all the reactants that we started with, meaning if we had 100 grams of coal and oxygen in total reacting together, then we have a total mass post-reaction of 100 grams. And this is, of course, assuming that our reaction occurs in like a nice closed container. Nothing's escaping. Mass is conserved. Okay, let's look at another question. If 76.2 grams of the contents in the container our other combustion products, and any leftover reactant, but we'll get to that idea much later. What mass of water vapor was formed? So we know, based on the law of conservation of matter, that the total mass in our post-reaction container equals 100 grams. And we know that inside our post-reaction container, we have present combustion products, one of which is water vapor, and potentially any leftover reactants, although for today, we're going to go ahead and ignore that, even though we see this up here as a little lump of coal left over. So we're going to save this idea for later. Okay, let's go back to the question. If 76.2 grams of the contents in the container are the other combustion products, so I know now some information about my combustion products that are not water vapor. So I have 76.2 grams of other combustion products. So this is 76.2 grams. What mass of water vapor was formed? So I'm trying to figure out how much of this was made, given what I know about our final mass inside our flask. All right, let's go back up to our little product container here. We know that inside here we've got some gaseous combustion particles that are what I'm calling our combustion products. And then we've also got some water vapor. Inside the container. And we know that the mass of these should in total give us the 100 grams that we have in our product container because we started with 100 grams of reacting material. So I'm going to restate this by saying that my 100 grams of my 100 grams of my total products minus the 76.2 grams of, let's go ahead and call them non-water products, has to be equal to the mass of water products. So let's see here, that would be 23.8. Someone please tell me later if I get that wrong. Grams, that makes the difference, and that difference is going to be the mass of water. So the law of conservation of mass in a chemical reaction is just following the law of conservation of matter in a chemical reaction, because by definition, a chemical reaction is simply the rearrangement of atoms. We are not creating new atoms, nor are we destroying old atoms. Now, this is still true even for like the technicality cases where we have radioactive decay. but we'll talk about that in Chem 220. All right. So we have done our warm-up. Let's go on to our next topic, which is how we can ensure that all of our how all of our chemical equations are obeying this law of conservation of matter or law of conservation of mass. And this is the process that we call balancing chemical reactions. So we will balance chemical reactions in video 2 coming up.